Welcome to MatSci Simple, where complex engineering and science is broken down into simple, clear, visual explanation. New episodes every week. Hit subscribe so you never miss one. Welcome back. In our last episode, we covered the fundamentals of metals. Today we go deeper. We are covering the stress-strain curve, heat treatment, the iron-carbon phase diagram, corrosion, grain boundaries, hardness testing, and fatigue. Every single one of these appears in GATE every year. This is university-level material science, explained simply. When engineers need to understand how a metal will behave under load, they perform a tensile test. A sample is gripped at both ends and pulled apart while stress and strain are recorded. The result is the stress-strain curve, the complete mechanical biography of that material. The horizontal axis shows strain, deformation as a fraction of original length. The vertical axis shows stress in megapascals. Starting from zero, the curve rises steeply in a straight line. This is the elastic region. Stress is proportional to strain, Hooke's law. Remove the load here and the material springs back completely. The slope of this line is Young's modulus, the material's stiffness. For steel, approximately 200 gigapascals. Then the curve reaches the yield point. Permanent deformation begins here. Beyond yield, the material enters the plastic region and actually gets harder with deformation. This is called strain hardening. The curve climbs to the ultimate tensile strength, the maximum stress the material can carry. Beyond UTS, the sample necks. One region becomes thinner and finally fractures. For ductile metals like mild steel, you get a cup and cone fracture with significant plastic deformation. For brittle materials like cast iron, flat, sudden, no warning. One test. Watch how the curve builds itself. The steep elastic region first. Hooke's law, perfectly linear. Then the yield point where the slope changes. The plastic region where the metal hardens as it deforms. The peak at UTS, then the drop as necking begins. And finally, fracture. Every region, every point tells you something different about how this material behaves. Read this graph and you understand the material completely. Here is one of the most powerful ideas in metallurgy. The exact same steel, same composition, can produce completely different mechanical properties simply by controlling how you heat and cool it. Four main processes. Annealing, heat to around 900 degrees Celsius, then cool very slowly inside the furnace. Large grains form. The result is soft, ductile steel, with hardness around 120 to 180 Vickers, used for wire drawing, sheet forming, and machining. Normalising, same temperature, but cool in still air. Finer grains, better properties than annealing. Hardness 150 to 220 Vickers, used for structural steel and forgings. Quenching, heat to austenitizing temperature, then plunge into water or oil. The rapid cooling traps carbon atoms inside the iron lattice before they can diffuse out. The result is martensite, body-centered tetragonal structure, extremely hard, 600 Vickers and above, but brittle, needs tempering. Tempering, after quenching, reheat to between 150 and 600 degrees, then air cool. Small carbide particles form. Brittleness reduces. Hardness falls to between 300 and 500 Vickers, but toughness is restored. Used for springs, gears, and axles. The key insight, hardness and toughness are always in tension. Heat treatment gives you the control to find the right balance. Watch the crystal structure transform. At 900 degrees, the iron is face-centered cubic austenite. Carbon atoms dissolved and mobile. Now we quench. Temperature drops rapidly. The carbon atoms have no time to escape. They get trapped inside the lattice. The structure distorts into body-centered tetragonal, stretched along one axis by the trapped carbon. This is martensite. The distorted lattice makes slip almost impossible. That is why it is so hard. And that is why it all iron-carbon phase diagram. Every metallurgist has this diagram memorized. The iron-carbon phase diagram is the fundamental map for understanding steel. The horizontal axis shows carbon content from 0 to 2.5%. The vertical axis shows temperature from 600 to 1600 degrees Celsius. Every point tells you what phases are present at that composition and temperature. The large central region is austenite, face-centered cubic iron, stable at high temperatures. Below it, the green region is ferrite plus pearlite, the typical room temperature microstructure of most steels. The critical horizontal line at 723 degrees Celsius is the A1 line, the eutectoid temperature. This is the most important temperature in the diagram. Heat above A1, austenite begins to form. Cool below it, austenite transforms to pearlite. The A3 line is the upper boundary for steels below 0.77% carbon. Above A3, the steel is fully austenite, where A1 and A3 meet at 0.77% carbon and 723 degrees is the eutectoid point, the most important single point on the diagram. Steel at this composition transforms directly from austenite to 100% pearlite on slow cooling. Every heat treatment cycle starts here. This diagram tells you what temperature to use and what microstructure you will get. Okay, let's understand the corrosion. What is it and why this is happening? Corrosion is the spontaneous deterioration of metal through electrochemical reaction with its environment, and it is extraordinarily costly, approximately 3% of global GDP every year. That is roughly $2.5 trillion in damage, maintenance, and replacement. The fundamental reaction is shown on screen. Iron at the anode loses electrons to form iron 2+ ions. Those electrons flow through the external circuit to the cathode, where oxygen and water combine with electrons to form hydroxide ions. The hydroxide ions meet the iron ions and form iron hydroxide, which converts to rust. This is a complete electrochemical cell. 4 strategies fight it. Galvanizing. Coat steel with zinc. Zinc is more reactive, so it corrodes first, sacrificing itself to protect the steel. Even if scratched, zinc continues protecting the exposed steel around it. Stainless steel. Add more than 10.5% chromium. An invisible chromium oxide layer forms and self-repairs if damaged. That is why kitchen utensils do not rust. Paint and coatings. Physical barrier between metal and environment. Effective until damaged. Cathodic protection. Attach sacrificial anodes of magnesium or zinc, or apply an external electrical current. The structure is kept as cathode and protected. Used for pipelines, ship hulls, and offshore platforms. The best systems use all 4 strategies together. Watch the process happen in real time. Iron 2+ ions leaving the anode surface and entering the electrolyte. Electrons flowing through the external circuit from anode to cathode. Hydroxide ions forming and migrating toward the iron. And at the iron surface, the rust layer building up with every cycle. This is happening on every unprotected piece of iron around you right now. Every unprotected railway track, every ship hull, every bridge without a corrosion management system. This is why corrosion engineering, grain boundaries, and Hall-Petch relation. When you look at steel under a microscope, it does not look like one perfect crystal. It looks like a mosaic, millions of tiny crystals called grains, each with its own orientation, packed together. The boundaries between them are grain boundaries. And grain boundaries are one of the most powerful strengthening mechanisms in metals engineering. When stress is applied, atomic planes try to slip. Dislocations, defects in the crystal lattice, are the mechanism of that slip. But when a dislocation reaches a grain boundary, it cannot cross into the next grain. The orientations are different. The dislocation stops. More stress is needed to continue. More grain boundaries means more stopping points. More stopping points means stronger metal. This relationship has a precise equation, the Hall-Petch relationship. Yield strength equals sigma 0 plus K times d to the power of -1/2, where d is mean grain diameter. As grain size decreases, yield strength increases. Engineers control grain size through processing, faster cooling, controlled rolling, or microalloying with small additions of vanadium, niobium, or titanium which pin grain boundaries and prevent growth. Watch the dislocation, the inverted T symbol, moving freely through the left grain. Now watch what happens as it approaches the boundary. The next grain has a different orientation. The dislocation cannot pass. It is blocked, stopped at the boundary. This is the Hall-Petch effect in action. This is why fine-grained steel is stronger than coarse-grained steel. And this is why every steel mill in the world carefully controls the grain size of every heat of steel it produces. Now, we understand how the hardness can measure. Hardness is the resistance of a material to permanent indentation. 3 standard methods. Vickers, a diamond pyramid with a 136-degree included angle pressed into the surface. You measure the diagonal of the square indent. HV equals 1.854 times force divided by diagonal squared. Works on everything from soft aluminium to hardened tools to ceramics. The most versatile method. Brinell, a hardened steel ball 10 millimeters in diameter under large force. You measure the indent diameter. Best for coarse materials like castings and forgings, where a large indenter averages over multiple grains. Rockwell, you measure the depth of penetration directly and read hardness straight off the dial. Fastest method, used in production environments. Looking at the comparison, annealed mild steel sits at 120 to 180 Vickers. After quenching, hardness exceeds 600 Vickers. After quenching and tempering, you can dial in exactly the hardness you need for your application. Fatigue and fracture. Approximately 90% of all engineering component failures are caused by fatigue, not by a single overload, but by repeated cyclic loading at stress levels well below yield strength. The SN curve on screen shows stress amplitude against cycles to failure on a log scale. For steel, the curve flattens at around 1 million cycles. Below this level, the endurance limit, typically 200 to 250 megapascals for mild steel. The material can theoretically withstand infinite cycles. Aluminium has no endurance limit. It will eventually fatigue at any stress level. This is a critical design difference. Fatigue happens in 3 stages. Stage 1, crack initiation. A microscopic crack nucleates at a stress concentration, a scratch, notch, inclusion, or surface defect. Stage 2, crack propagation. With each cycle, the crack advances a tiny amount. The fracture surface shows characteristic beach marks, concentric curved lines showing where the crack front was at different times. Under a scanning electron microscope, individual striations appear, one for each cycle. Stage 3, final fracture. The remaining cross-section becomes too small and the component breaks suddenly, often with no visible warning. To improve fatigue life, eliminate stress concentrations. Shot peening introduces compressive surface stress that resists crack opening. Smooth machine surfaces and generous radii at all section changes are essential design rules. Real-world structures, 4 structures, 4 different alloys, 4 different engineering challenges. The Eiffel Tower used wrought iron, not steel. Ductility was essential for assembling 18,000 prefabricated parts on site. Brittle cast iron would have cracked. The tower also expands 15 centimeters in summer, deliberately accounted for in the original design. The Golden Gate Bridge used high-tensile carbon steel cables with an ultimate tensile strength of 1,600 megapascals, 4 times ordinary mild steel. Without that strength, spanning 1.3 kilometers of water was impossible. Jet engine turbine blades operate above 1400 degrees Celsius, above the melting point of ordinary steel. The solution is single crystal nickel superalloys, not polycrystalline, single crystals with 0 grain boundaries, because grain boundaries are sites of creep and failure at extreme temperature. Internal cooling channels carry compressed air through the blade wall, keeping metal temperature below its melting point even though the surrounding gas is hotter. Railway tracks use high-carbon paralytic steel at 0.7 to 0.8% carbon, hardness 260 to 320 Brinell. Rolling contact fatigue is the dominant failure mode. Head hardening creates a harder wear-resistant surface over a tougher core. Same principles of materials science applied at the extreme limits of what is physically possible. Let us bring everything together. The stress-strain curve reveals Young's modulus, yield strength, UTS, ductility, and toughness from one tensile test. Heat treatment, annealing gives softness, normalizing gives uniformity, quenching gives hardness, tempering restores toughness. The iron-carbon diagram, A1 equals 723 degrees Celsius, eutectoid at 0.77% carbon. Every heat treatment starts here. Corrosion is electrochemical, iron as anode, oxygen at cathode, moisture as electrolyte. Fought by galvanizing, stainless alloying, coatings, and cathodic protection. Hall-Petch yield strength equals sigma 0 plus K times D to the minus half. Smaller grains, stronger metal. Fatigue causes 90% of engineering failures. 3 stages: initiation, propagation with beach marks, fracture. Steel has an endurance limit. Aluminium does not. In the next episode, Metals Part 3, we go into alloy design. Thousands of steel grains, aluminium alloys, and superalloys, how engineers design them from first principles. If this video helped you, please like and subscribe. Drop a comment with your answer to today's quiz. Why does quench steel need tempering, and what would happen if you skipped it? Best answer gets pinned.